Hello, everyone. Welcome. My name is Maarten van Dantzig. I'm a security engineer with Google, specifically working in digital forensics and incident response.
And I'm Alex. I work in privacy and security research.
All right, cool. So without further ado, what we'll be discussing today is an AI agent that is capable of doing log analysis, basically. And what we'll also discuss during the presentation is how we've implemented it into Timesketch. And we'll go into what Timesketch is, etc., further into this talk. But before we start, just a quick pop quiz that I wanted to do. If I say 4 million in the context of the fact that it is like a digital forensics and incident management talk, what do you think 4 million would refer to? Any guesses? Don't want to put anyone on the spot. So it's the average number of events on a freshly installed like Windows server. So my point here is that before you've even done anything on a system, there are already 4 million events that have taken place that are potentially relevant to investigate for an analyst, someone working in the SOC, digital forensic analyst, incident responder. And that's a lot of data to look at. I have a slide later that explains further what the 4 million entails, but this sort of shows the problem that we have as forensic analysts, and I think it's a great opportunity for AI to help us like cut through the weeds. So before I go over the agenda, the QR code here you can scan like right now, and you can already get access to the slides. The QR code will be there again at the end of the presentation, so you don't have to scan it right now, but you'll be able to follow along now or see all the slides after. So the agenda. The log volume problem, this is the 4 million number I just referred to. That's what like we'll be speaking about and what the issue is that we're trying to solve. And I'll go into a bit more details there. Then to get everyone on the same page, I'm going to do a little bit about Forensics 101 at like a high level and how we do it at Google. Then we'll go into the agent that we built, like go into the weeds, all the technical details, etc. We'll show you how we've implemented it into Timesketch, our log analysis platform, and then we'll show you how well the agent performs by showing you some metrics. All right, so back to the log volume problem. So this is the 4 million events I was referring to. Like if you would take a Windows 2022 base image and you'd parse all the events that have happened there, there's 4 million, right? And 3.1 million of those are made up out of like file system activity, modifications, deletions, etc. Then you have 400,000 registry events, 350,000 use-end journals. Like there's a lot going on, and this is on a system that hasn't even been used yet. So once you start using it, of course, there's going to be even more logs there, and this is without accounting for like EDR solutions that produce even more logs, process execution, etc. So this is the problem we're facing as analysts. I think I can best sum up the log volume problem in these 3 categories. So the signal's buried in the noise, right? Like it's finding the needle in the haystack, that's the challenge. All the logs are also different. So if you have a security analyst or a forensic expert, they can't all be experts in like the same log sources. So web server logs look very different than Windows event logs, and you can't expect everyone to be an expert at every type of log. So that's another issue. And then the third one is that, and this is, I think, an increasing issue, is attackers are looking like normal users more and more. So attackers are abusing tools already on the system, right, like living off the land tools to sort of hide their activity. And these 3 things combined make for a difficult job. All right, so taking a step back first, so that we're all on the same page as to what is forensics, at least for now during this talk. Let's classify it in like collection, processing, and analysis. So with collection, whatever tool you're using, you're fetching artifacts, you're getting a disk image, you're then processing those into like some type of normalized data, and then comes the analysis. And how we're doing this as Google, just to name a few examples, is for collection, we would, for example, use libcloud forensics. So libcloud forensics is an open source tool that works for most of the major cloud platforms that lets you easily get artifacts from those cloud providers. So this is a whole disk image, or for example, logs from like a cloud console. We would then process that with Plaso. This is another open source tool that we maintain. It's basically like a super timelining tool and parser of like all sorts of relevant artifacts. Then we take those Plaso files and we throw them into Timesketch. And Timesketch is like our collaborative timeline investigations tool. And what I'm trying to show on this slide is that we can go from like a disk image in a cloud platform, let's say it's GCP, to events in Timesketch using only open source tools. And that's pretty cool, because anyone can use these tools and basically achieve the same thing. There's of course all sorts of other things you could use, like another analysis tool. Many would use that not open source would be Splunk, but we tend to use Timesketch. And then to make our lives a little bit easier, it's just one more tool. There's a fourth tool that we call dfTimewolf. And the idea is that dfTimewolf has several recipes that you can execute. It's one command, and it automates like the usage of all these free tools. So what you see here is like a dfTimewolf recipe called GCP Forensics Timesketch on a GCP project. So in this case, the name of the GCP project is MVD GCP project. I just enter dfTimewolf, the recipe name, and then my project name. It gets the disk image from GCP, so the GCE disk image, throws it into Plaso. Plaso parses all the relevant artifacts, or the things are relevant, and then we throw that into Timesketch. And then from there on, our analysis starts. So we'll be focusing the remainder of this talk on Timesketch, on the analysis part. This is a quick screenshot of what it looks like. I have a couple of videos and images after. But it's basically, it allows you to analyze all the artifacts and events from a file system collaboratively with other analysts. So you can leave comments on specific events, you can star them, say they're bad, suspicious, good, all that sort of stuff. So let's take you through a practical example of what this may look like. This is an example email that customers that run a GCP project could receive from us. So if we detect abuse of like cloud resources, then this is the email that they would basically get, saying we have a suspicion that your project is being abused, for example, for coin mining or other activity. And this is the metadata that you can use to run that investigation. So this is the project where we'd want to get the logs from. We would use Plaso to parse all the artifacts, and then we'd send those artifacts to Timesketch, and then hopefully we can use the specific timestamps that are mentioned in the email to filter specifically to the activity that we're interested in. So this is what Timesketch looks like. This is the first view that you get. The colors at the top, it's a little bit small, but the colors at the top, there's like 3 of them, starting with purple, are like timelines. There are specific sets of artifacts that you've imported. And then I'll show you what Timesketch looks like in action. So here someone just searches for star, which means you're searching for all the events. And then this is someone scrolling through those events, sorting by time. And when you click on an event, you get like all the context of that specific event, and then you can do sort of whatever. So if we take the email from 2 slides ago, where it said like, abuse on the GCP cloud project, and these are the times, you can then enter those times as like a time interval in Timesketch and zoom in specifically on that time set. So this is like a time of 6 hours apart, and then you can search for that. The thing is, on most systems, and this is the log problem I showed you before, there'll be a lot of logs. So even searching for 6 hours on this specific system will still give you around almost 8,000 events. And that's a lot to manually go through. And with the help of AI and LLMs, we can already see some of the benefits in making this more efficient to go through. And I'll show you an example of a feature that we recently added to Timesketch that does this. So this is someone looking for that specific time interval. And I'm pressing search. And then you see a little AI summary at the top that's like loading a summary of all the events that are in view. And this works for up to 500 events. So 500 events at a time, you can click through Timesketch, and instead of scrolling through all the events at the bottom, there's a reasonably, there's a pretty good summary at the top that'll tell you what those 500 events entail, basically. And this will click through a couple of times until the analyst sees an event that they deem to be relevant. Scrolling to the event. And then here's a particularly interesting event, or potentially interesting event, where someone's replacing like a cron tab on the system, marking it as suspicious, and then adding a comment why they think that this specific event is suspicious. And then all other people working in that same sketch can see the analysis and basically work together. Then you can also do a context search. So around that specific event, show me 60 seconds before, 60 seconds after, and there the summarization feature also works. So this has been very useful. Like this really helps at least our analysts get up to speed on those events much quicker than they would have been able to before. But there's a couple of problems with this. Like if you want to think bigger and really use an AI or an LLM to do this properly, this doesn't work so well because you still need to click through like all the pages. Like you're essentially still trying to find the needle in the haystack yourself, but you can just do it a little bit faster. So the next thing that you could do is like send all the logs to an LLM model on like a chunk basis. But if you're doing this in chunks and you're sending them all at the same time, to save speed, every chunk has like its own context window, and like the various chunks don't know about each other what they know. So there's no reasoning across them. So that's the limited reasoning part. And then of course the second issue is it doesn't scale so well. Like just sending millions and millions of logs to state-of-the-art Gemini models, or whatever type of LLM model you might use, costs a lot of money, doesn't scale, and it's not very efficient. So we need a smarter solution. Alex?
Thank you. All right. So let's talk about SecGemini for a second. So SecGemini is an experimental research model and program in general. And I want to be very clear that GCP already has offerings on mature or productionized SecOps agents. SecGemini is not yet at that level. SecGemini has various capabilities, but the one I want to talk to you about today is reasoning on logs. So this is what we've built into SecGemini, a general logs reasoning ability that is capable, scalable, and autonomous. So we want to use this capability for at least two things: investigation and detection. So investigation is what we previously mentioned, timeline reconstruction. You start with an alert, and you're trying to figure out what happened. Detection is unsupervised threat hunting. So you are just telling the agent to look at all the available logs and find any evidence of compromise and explain it. SecGemini's ability is also designed to be scalable and flexible. So we want to operate on massive amounts of logs, hundreds of millions of log records, but also of all different sorts and different types. And also finally, and that's quite important actually for us as security practitioners, we need to be sure of the findings. So we need this whole thing to be easy to explain and verify. So let's see how we do this with SecGemini. So at first glance, this looks a little bit of a easy problem perhaps, because on one side, you have the raw logs to analyze. Let's say you have hundreds of millions of events. And on the other side, you have a backbone LLM, in our case, Gemini. So at this point, you might say, okay, well, can I apply the classic React loop agent approach, which is basically equip the LLM with a tool so that the LLM can access the logs, like fetch some records at a time, and then reason on those records, and continue that in a loop. So that might be our first thought. There are at least three problems with this thought that makes it not work. The first problem is that the context window is still quite limited, even in Gemini, production Gemini. So if you keep on fetching log records from those hundreds of millions of records, you're going to clog that window very, very quickly. And you're going to fill that in a few steps. So you don't have a lot of iterations available to you. The second limitation is, and that's really an experimental observation, is that if you keep on adding previous log records to the context window, the LLM eventually loses its ability to reason and loses track of where it is and what it's trying to accomplish. And finally, and that's quite important for us, as I mentioned, this whole thing is quite hard to follow as a human being because you have to parse through hundreds of pages of free-form text that gather both LLM outputs and log records. And that's really hard to comprehend. So we have to abstract away from the base text representation of these interactions. And for that, we're going to introduce what we call an exploration graph. And that's going to serve us as the memory for the agent. And the exploration graph is going to store or represent the state of the investigation. In this graph, an edge means a logical entailment. So between two nodes, it means that one node is a specialization of another node, is an analysis of, or an answer to, etc. You'll understand that in a second with some examples. There are 4 node types. First, there are investigative directions. So these are goals that the agent creates for itself and wants to accomplish. You can see that some investigative directions depend on each other. That's logical entailment. The second operation, or the second type of nodes that you have here, are fetch records. So this is basically our tool call, or tool calls. And these also depend on, logically depend on goals. Almost finally, we have written summaries, what we call observations of the fetch log records. And finally, if we're lucky, we do have investigative finding nodes that also depends on what we just fetched. So the role of the LLM in all of this is to update the exploration graph. That is all the LLM is doing. So to update the exploration graph, the LLM adds nodes. And again, that is all it's doing. So in the first phase, the LLM is going to propose general investigative directions, and that's all it's going to do. In the second phase, the LLM is going to write the correct tool calls to make progress on those investigative directions. In the third phase, the LLM is, you guessed it, going to observe the results and write little summaries and append those summaries to the graph. And then we're going to repeat this process, and we're going to build the graph iteratively until we find some conclusions. I'll give an example of that. So here's the setup. Imagine you have a detection signal that triggered on a Linux VM. The first thing that you do, as Martin mentioned, is you're going to image the disk, and you're going to extract all the logs available on the system, like everything you can find. In this particular example, it's not that big. It's just 1 million log records and 7 different log types: syslogs, file system, basically stats, and secure Linux logs. And finally, you're going to prompt SecGemini to perform a blind investigation, in the sense that you're not going to give it any starting point. You're going to say, find and explain all attack actions. And that's the goal that the agent is trying to accomplish. So in order to see how this works, let's look at the exploration graph that is being built by SecGemini. So as I mentioned in the first step, we create investigative directions. Here, the model comes up with 3 directions. By the way, I forgot to mention, but in the very initial prompt, we tell the LLM about the available logs. So we tell the LLM that, oh, there's 1 million log records, and there's like these 7 different log types, and that's all we say. And here, we have those 3 interesting directions. The first one is, they're, I think, quite easy to understand. They're quite vague and high level, because at this point, we don't have a lot of information. But you can see that, for example, in the first one, the LLM is suggesting to, well, look at all the connections that were made through SSH, the machine. All right, so if you remember from the last slides, the next thing we're going to do is we're going to have the LLM call the fetch tool to collect the relevant logs with an intent that is compatible with the investigative directions. So I'm not going into the details here for the fetch tool, but there's more behind the scenes here. And finally, to complete the general update for this phase, the LLM is going to write summaries for the results it obtained. So in this particular example, I'm not going to show the 4 summaries. I'm just going to summarize this one, and that's what the LLM has in the graph. So the LLM observed that there's a successful root login at a particular time. Actually, multiple successful logins. All right, then we repeat the process. Then we ask the LLM, okay, what are the best next investigative directions to pursue? So this is what Gemini comes up with. It's, I think you would be familiar with this reasoning. It's essentially pivoting around the time of the SSH logins. So it's trying to see what happened before or after those logins in other logs. And it's doing it all by itself, like we're not guiding it in any way. So again, we're going to write some fetch calls to fetch those particular records. And we're going to write some summarizations of those results. And here, we got very lucky, because this is a small example, and I wanted everything to fit in one slide. The LLM finds, indeed, very suspicious actions and activities around those root SSH connections, including a modification of, including persistence activity here, the cron jobs, and as well as suspicious files. The thing that I also want you to notice here on this slide are those lines, are those numbers next to the log types. Those are log record lines. This is how we also get explainability and verifiability in the system, because we have the exact reference of the logs. And what the graph gives you here is the ability to go back in time and figure out how did the LLM find that, made that conclusion? How was this found? All right. So here are the takeaways. Together with the exploration graph, Gemini, within Gemini, is able to process hundreds of millions of log records and handle complex multi-step investigation processes. At every round, the LLM only sees a relatively small amount of the logs. The solution is also explainable because you can, at the end of the process, you have an exploration graph that explains the entire reasoning chain that led to the results. And finally, the process is also verifiable in the sense that you have the reference to the log records. And with this, I'll pass it on back to Martin.
Yes, so this is one thing, is just like having this very smart agent in the background do the investigation for you. The second thing is, how do you make this apparent to analysts? Like, how do you integrate this into the tools that you already have so that the analysts actually can verify the results and trust that, you know, what this agent says has happened has actually happened. So that's what we set out to do. So we ran multiple like user studies of like analysts that we would want to work together with the AI and ask them like, what would you want to see from the AI, or like, what are the most important parts of your workflow when you're doing, you know, your analyst job. I'm not going to go over each and every one of these, but I have a next slide where we'll zoom into some of them. So first, to show you a short video of what this currently looks like in Timesketch. It's a bit small, but basically what this is a completely separate view in Timesketch called the AI view, where you can see the agent as it works and the results are sort of streaming in. So what you see on the left in small are like hypotheses or like investigative questions that the agent has come up with that is asking itself about the logs. And then if it sees something related to them, it's going to link the actual events that it finds in Timesketch directly to those investigative questions or to the hypotheses. So here's a screenshot of like a fully ran, of a full agent run on the logs in a particular sketch. So again, what you see here on the left are the questions that the agent has proposed, that it deemed to be relevant to ask about this particular sketch or investigation. And then directly under it here, so we're zooming in on one question now, are the events that are in the sketch. So immediately you know that like these results were not hallucinated, like the results are right there, and you can then pivot from the events that the agent has highlighted directly to anything around the events as well. So this is really the needle in the haystack finding that you want. Like even if it just produces a single finding that's relevant, you can take that, do the context search, and find potentially other relevant events. What you then see at the top is a conclusion, and the conclusion is again comes from the agent, and the analyst is able to either accept or reject this conclusion. And in this way, the analyst and the AI, like the agent, are working together to build towards like multiple questions that are actually relevant, write a conclusion per question, and then finish the investigation with a full investigative report that contain either multiple questions from the agent, from the analyst, or a combination of the two. All right, the evaluation. Alex, you want to tell them how well it does?
Thank you. So this is an agent, and evaluating agents is very hard. I'm sure most of you are familiar with this. Nonetheless, we've tried, and I think we've done a reasonable job at it. So the first thing we need for evaluation is a data set, a labeled data set. So this is how we constructed it. We collected about 100 instances of compromised VMs on GCP. These are real-world cases. So the VMs were compromised by real-world attackers. And the detections are a result of what Martin previously showed. Things like very targeted and very low false positive rules. Things like, oh, this particular VM reached out to a suspicious IP, or this VM has been detected to have some coin mining operations. Right, so that's basically all you would know at that stage. I want in the next few boxes, I want to convey a sense of scale and the difficulty of the data set. The average case is relatively hard. Some are really, really hard. So on average, we have 15 different log types. Sometimes we have 50 different log types. These are also a mix of Linux and Windows VMs. There's, on average, about 4 million log records. Some have 100 million log records, and some have a lot less. And finally, and most importantly, this is the needle in the haystack thing, we have 38 annotated records on average per case. So it means that the human analysts, when they conducted labeling and investigation in each cases, they've identified on average 38 log records that bear the traces of the attacker. And finally, this is also to show you that these are not all the same instances. We've categorized the data set into multiple compromise type dimensions. You have all sorts of things in there. You have weak passwords that were brute forced, essentially. You have system misconfigurations that allowed for something to be open. You even have software vulnerabilities, unpatched software that's being exploited, leaked credentials, and other things. So let's go into the evaluation task. There's many ways to evaluate a system like that because a system like that is able to do a lot of things for you, basically. So here we wanted something quite close to what we would use it for. And the task, the evaluation task that we ask SecGemini here is to find all attack-related indicators or entities. I'll give a few examples. So these are identifiers that pertain to the attack. So URLs, file names, IP addresses, PIDs, executable names, etc. There are 3 levels of relevance for those: critical, important, and supplemental. So the critical entities are those that are most tightly attached to the attacker. The important ones are 1 level below, and the supplemental ones are, okay, it's nice if you get them, but you don't have to get them. So here's an example. This is from syslogs. So the color coding is per categories of relevance. You see that the most important indicator here is the URL that contains the IP and then the name of the script that's being downloaded on the machine. And then you have things that are really nice to have, like, oh, this is cron, and that's the PID of this process. And then you have things that you could do without, but they still should still be collected. So that dev null, for example. All right. And if you remember, we're able to do 2 things with SecGemini. We're able to do hinted and not hinted. So in the hinted one, we give SecGemini the initial detection information, and that's akin to timeline reconstruction, right? And the non-hinted evaluation, we are not given a starting point, we're only given the logs, and the mission here is to do thread hunting. So let's look at the results. So for the easier case, which is the hinted case, we collect more than 50%, or the agent is able to collect more than 53% of the critical indicators. So just a quick note, 53% might not seem high. It is actually quite high in practice when you see the agent work, because as a security analyst, as soon as you have one finding in any scenario, you can actually start your own investigation process and continue finding the other events in the log. The precision is at 12%. So 1 in 10 of our entities wouldn't have been labeled by the human experts as pertaining to the attack. There are two reasons for that. One reason is that there's obvious false positives. That's correct. And the other reason is that as humans, it's actually quite hard to be exhaustive and to look at and to find all the possible indicators. So what happens is that we are under-labeling. Our data set is under-labeled in the sense that we know that there are critical entities that are not labeled as such in the data set. So the precision is artificially low for that reason. Finally, and this is quite interesting and quite impressive, is doing well on the hinted, so timeline reconstruction, but it's holding its weight for threat hunting. So this was the kind of like the interesting surprise of this project. This thing is also able to perform autonomous investigations and threat hunting. The performance is slightly less, but it's still there and still quite usable at 47% recall on critical events. So there's two takeaways here from these numbers. First, the first takeaway is that SecGemini finds 53% of critical indicators across millions of log records, and the total cost for this currently is under $3. We expect this cost to go down. And the other thing that I was mentioning is that even finding one critical indicator is a big deal. And it turns out that in at least 90% or more of the cases, SecGemini is able to find at least one critical indicator. And Martin.
Thank you. Yeah, this is an example I wanted to give because these 100 cases that we run are like our investigations, right? Like you don't know much about them. So to sort of like give an example that more people in the room might be familiar with, we also tried to run the agent on like a public CTF or a challenge. So some of you may know this. This is a forensics challenge from a couple of years ago created by James Smith. It's hosted at dfirmadness.com. And the scenario is this, right? Like, so your boss comes in, says he's been contacted by the FBI and they found like his intellectual property on the dark web. Here's a bunch of data from like the network, go and investigate what happened. I think a lot of people do this challenge either for fun or they give it to like new hires at their company to like see how you can solve this. And like all the data is public and you can try to run this. There's several levels of difficulty that you can do this challenge with. And the most difficult mode that of course we tried to run with the agent is the disk image only. So I think it's like a disk image of a domain controller as well as not a server or a client, I'm not sure, but at least a domain controller. And when we parse that data with Plaso, put it into Timesketch, and then put SecGemini to work. And this is the recall on those. So including the scenario from a couple of slides back about being contacted by the FBI, saying what happened, we get 60% of critical indicators being found by the agent. It's also able to answer 22 out of the 30 questions that were asked by the CTF, despite not giving those questions to the agent. So like you can infer all the answers from those 30 questions, or at least 22 of them, by just looking at the output. Like it's smart enough to know what to look for inside those logs. What's more interesting, of course, like if you do not include the scenario and you just give it the parsed artifacts of those 2 disk images, it still performs really well. Like it's still able to answer 20 out of the 30 questions and still finds 50% of the critical indicators, which is a really good performance for like going at it completely autonomously and not knowing what the context is of the incident. Like this is real proper threat hunting. All right, so if you want to learn more, currently the agent inside SecGemini is available through a trusted tester program, so this is experimental. So if you want to try this out, you can scan this QR code or go to the link. As I said, the slides are available online, and request access to this. The Timesketch view, so the AI view that is in Timesketch, is public right now. So you can already use that to like run investigations and potentially like use an alternative agent or use SecGemini directly to interface that. Like that's open source. And what I also wanted to mention, because I forgot earlier on, like the summarization feature that is currently like in Timesketch, it's like sort of the simpler approach. You can run that without any like Gemini models as well. Like you could run a locally hosted LLM using Olama, and that would work equally as well. We'll do some demos as well at the cloud booth. We'll have a talk at Arsenal, and some of this will be part of the GenSec CTF that we were running at DEF CON. Great, here's the QR code again. If you want to get access to the slides, those are up right now. Any questions, you can of course email us directly. I'm not sure if we have much time for questions. In any case, we'll be at the rep room, Benley Bay, level 2. So we'll go there immediately after this talk, and I think you can just like follow us along, and we'll be available there to answer questions. All right, thank you very much.
Thank you.